Planet Earth is unique, an engineering marvel, driven by heat from within. The latest information from satellite maps, sonar and radar images have been brought together to create this, a virtual planet Earth. The Earth is a machine. This is how it works. The surface of our planet is restless and violent. Every day there are volcanic eruptions and damaging earthquakes. The Earth machine is in constant motion, driven by forces unleashed deep within. Most of the population live in towns and cities and have no idea what lies beneath the ground. If we lift up the sidewalk, what would we see? Gas pipes, water mains, and electric cables fill the first 100 feet below the surface. Most subway tunnels are no more than 200 feet below the ground. 300 feet down, the matrix that supports the city disappears. No human being has been more than 2.5 miles below the Earth's surface. The center of the Earth lies almost 4,000 miles below that. The Earth's inner core, a giant ball of metal. The core is almost as big as the Moon and as hot as the surface of the Sun. The inner core is the engine that drives planet Earth. It radiates heat, which rises back up to the surface. It's a process that began when the Earth was formed 4.6 billion years ago. At that time, the planet was a ball of super-hot lava. Over millions of years, it cooled and formed a thin crust of solid rock. A new type of lava erupted and burst through the cracks in the crust. This rock was lighter and formed plates that floated higher on the crust to create the areas that are now land. The lava also released something else. Two elements, hydrogen and oxygen, combined to create H2O, better known as water. The first oceans were formed. The Earth machine had created the outer surface of the planet. This virtual Earth shows how it works. Today, the surface of the planet, the bit we live on, is called the crust. If the Earth were an apple, the crust would be no thicker than the apple's skin, ranging from 3 to 45 miles thick. The crust covers the entire surface of the planet, including the seafloor. But it's not one single piece. The crust is broken up into 14 huge tectonic plates. The boiling heat below the crust, in the center of the Earth, keeps these plates constantly on the move, up to 6 inches every year. Millions of years ago, the North American tectonic plate shifted. Nothing dramatic, but enough to open up cracks in the Earth's crust, a few feet beneath the surface. Water seeped down into the cracks and eroded it to create one of the most incredible natural structures on the planet. Beneath the streets of the Sunshine State lies the Floridian Aquifer. The aquifer covers 100,000 square miles. It is a vast network of fast-flowing subterranean rivers, a precious resource that provides most of Florida's fresh drinking water, up to 3 billion gallons a day. So this aquifer has to be protected from building or farming developments that could pollute the water. This is a task for biologist Tom Morris and his team.
It's very important to map these underground caves because that's our drinking water. So the more we know about what's going on down in that aquifer, the better off we're going to be up here on top.
Tom and his team squeeze through cracks in the bed of the lake that leads to the aquifer. It's a claustrophobic dive. They must pass through holes in the rock, barely wide enough to wriggle through, followed by an 80-foot descent.
Down and down we go!
On the surface, a radio engineer maps the diver's exact location with a transponder system. It looks basic, but it can penetrate over 100 feet of solid rock and water. Far below, Tom has reached the aquifer.
Okay, I just busted into clear water.
A subterranean world. Unseen, unmapped beneath the golf courses, parking lots, and shopping malls of Florida. The aquifer extends under the whole of Florida and into 4 other southern states. Around the world, there's more water held in underground aquifers like this than in all the lakes and rivers on the surface.
The current is pretty strong down here. It's ripping on by.
Above, the engineer records their route, wherever it takes them. After half an hour, another section of the Floridian aquifer has been successfully surveyed. Now the divers must either retrace their path or find an exit before their oxygen runs out.
Now moving. Yeah, we stopped here.
A shaft of light shows the divers the way to a new exit through the roof of the aquifer.
This is very useful to us. We can now, instead of getting in 1,500 feet or so back that way and bucking that strong flow and using so much air up, we can come here and start fresh and head on upstream. That's going to be so useful for us for mapping this underwater cave system, and we can put this cave on the map.
The virtual Earth in the hangar shows how the Earth machine creates powerful effects on the surface. The tiny cracks in the ground in Florida are caused by stresses within a single tectonic plate. However, when two tectonic plates crunch together, they create huge splits in the ground called faults. February 22nd, 2011. The cathedral spire in Christchurch, New Zealand falls as an earthquake leaves 182 dead. Less than a month later, on the 11th of March, an even bigger earthquake struck Japan. It produced a tsunami with waves of up to 98 feet high, killing perhaps 25,000 people. And on the other side of the Pacific, just a year earlier, 562 people died in a powerful quake in Chile. The Pacific Rim is an area of intense earthquake activity. In just the last 50 years, there have been dozens of major earthquakes all along the coast of North and South America. This is the Memorial Stadium, home to the Golden Bears. It's one of college football's oldest and most iconic arenas.
Let's go, let's go, let's go, let's go. Let's go, let's get up there, let's go. Go. Head up now, go. Good.
But the stadium is in trouble. Stands have crumbled, bleachers bent out of shape. A fault line runs right underneath the stadium, from goalpost to goalpost. The Bears must protect the stadium from future earthquakes. They've taken drastic action. They've split the stadium in two, right down the line of the fault. Roland Bergman is a geologist at the University of California, Berkeley. He has monitored the fault line for years.
So I'm standing pretty much right on the fault. This side of the fault is moving this way, whereas this side of the fault is moving this way.
But the fault is not moving fast enough.
The fault slip we see every year is about 4 millimeters per year, and that's about half of what we would expect based on long-term measurements.
The two plates on each side of the fault should have moved further, which means deep below ground, pressure is building. One day, that pressure will be released in a sudden, huge movement of the Earth's plates. An earthquake.
So half the slip is not happening, and eventually has to catch up in what we believe is a large earthquake. And we think it's going to be a really large earthquake.
To make the stadium earthquake-proof, the bears will put two parts of the stadium on separate free-floating blocks of concrete, so that if a quake hits, the stadium will survive.
So this side of the stadium is going to be completely separate structure, separated from this side, and the two sides can move independently, even in a large earthquake. The two sides of the stadium are just going to move their separate paths, and thereby there will be much less destruction.
The work will take 2 years to complete and will cost $320 million. The last major quake on this particular fault was 140 years ago. The next one is due anytime soon.
The next big earthquake is going to be an unimaginable disaster. Millions of people moved here since we've had an earthquake of similar size, so the number of lives lost and the damage is just going to be incredible.
When the next earthquake hits the Bay Area, this place at least will be safe.
At least with the work that's being done on the stadium right now, this is going to be one of the safest places to be in the next large earthquake.
Roland Bergman takes to the air to survey the fault line. The fault that is pulling apart the Golden Bears Stadium is called the Hayward Fault. It's part of one of the most famous geological features in the world, the San Andreas Fault. The whole fault system runs 800 miles from the south to the northern coast of California. Earlier quakes along the San Andreas Fault tore the land apart.
So now we're right straight over the San Andreas Fault, and the lake that's right below us, Crystal Springs Reservoir and San Andreas Lake, essentially stretched along the fault line. And the lake is so long and skinny and straight because the valley was formed by the fault. The fault is just grinding up the rocks, eroding out the valley, and that's why we have the lake here.
Back in the hangar, the virtual Earth displays earthquake data from the last 50 years. This shows clearly that the world's largest fault lines lie between the planet's tectonic plates. A fault needs to shift only an inch or two to cause a quake, but over millions of years, the land can move big distances. Rocks found here in Northern California started out hundreds of miles away in Southern California. Changes to the future landscape will be dramatic. In 9 million years' time, there will be no need to drive the 380 miles from Los Angeles to reach San Francisco. The two towns will be side by side. Tectonic plates are in constant movement. Sometimes they creep or slip past each other. At other times, the plates collide head-on. Then the land buckles upwards to create mountain ranges like the Alps. $50 million years ago, the continental plate under India collided with Asia. The result was the greatest mountain range on Earth, the Himalayas. And its highest peak, Mount Everest. At 5.5 miles above sea level, it is the highest point on the planet. The tectonic plates that created the Himalayas are still pushing together. so Everest grows by 0.2 of an inch every year. Back within the hangar, the virtual Earth shows how the Earth's crust is split into 14 colossal tectonic plates, all of them on the move. They slide by one another, creating earthquakes, and collide with each other, creating mountains. But they also move up and down, creating entirely new land. This is Alaska, land of sweeping glaciers, big skies, and eternal snows. The land here is on the move. This time, it's going up. This is the Mount Fairweather Golf Course on the edge of Glacier Bay National Park. It's popular with local golfers. The game would have been impossible 50 years ago. The players would not have been walking from tee to tee, they would have been wading. The land they're playing on was very recently underwater. Sierra Willoughby is a ranger in the Glacier Bay National Park. A few hundred feet from the shore, there's a cabin. Nothing strange about that. Except this cabin used to be on the waterfront.
If you were here when this cabin was first built a few decades ago, you'd be able to sit on this porch right here and look out across open water to see the Fairweather mountain range on a clear day.
So what happened? Where did their view go? During the last ice age, the whole area was covered by a sheet of ice. When it melted, the Earth's crust no longer had to bear the enormous weight of the ice. The land is now springing back up again. The cabin may have lost its view, but the Mount Fairweather golfers get a little more golf course every year. The Earth's crust covers the entire planet, a total surface area of nearly 200 million square miles. The movement of the crust creates many different landscapes. And, it would appear, many different types of rock. But this is an illusion. Fundamentally, the Earth machine makes the entire crust from only 3 basic types of rock. North Carolina, the largest open-faced granite quarry in the world. 83,000 tons of rock are hacked out of this 60-acre site every year. The granite rock found here is called igneous. Igneous rocks make up 90% of the entire crust and are formed when magma cools. Then there are sedimentary rocks, like limestone, the remains of ancient seabed crushed flat. The third kind of rock is called metamorphic. Marble is the best known. It's what you get when you heat and crush limestone. These 3 kinds of rock make up the entire surface of the world. The Earth machine creates molten rock. If we remove a piece of the crust, we can see the furnace that produces it. This is the mantle. The mantle is over 1,800 miles deep and up to a blistering 2,200 degrees Celsius. This furnace is the source of all the lava from the Earth's volcanoes. The molten rock formed in the mantle is hot and light. It forces its way up into the Earth's crust. It collects in huge underground chambers. Combined with gases, it becomes explosive. It blasts up through the crust and erupts onto the surface. Most volcanoes work this way. They are fed by underground chambers of magma around 10 miles below the surface. However, there are a few exceptions. Mount Nyiragongo in the Democratic Republic of the Congo. In 2002, the volcano erupted, killing 147 people. It's one of the most active volcanoes in Africa. It towers 2 miles above the surrounding countryside. At the bottom of the volcano's crater is a boiling lake of lava over 750 feet across. The temperature on the lake's surface is nearly 800 degrees Celsius. This lava comes from deeper underground than almost any other volcano on the planet. Some scientists think the lava may come from a column of superheated magma from deep down within the mantle. Dario Tedesco is one of the world's leading authorities on Nyiragongo.
It's really completely different from other volcano. It really is unique. There are so many secrets on this volcano that you don't get from the other volcanoes.
Dario leads a team of scientists into the crater. They're here to get a sample. The team must descend from the smoke-shrouded rim of the volcano into the searing heat of the crater. The crater is deep, very deep, deep enough to accommodate the Empire State Building. It's a treacherous, crumbling incline. The ground can give way at any moment. The crater has 2 ledges. The team now approach the second. They must abseil down a sheer wall of rock, a drop of over 600 feet. As the team edge closer to the lava lake, the danger increases. There are huge cracks in the ground. Sulfurous fumes pour out from below. The journey has taken several hours to reach level ground. It's getting dark. Time to make camp. While the team sleep, the superheated molten rock in the lake churns and boils continually, spilling over the rim. Nyiragongo is one of the most active volcanoes in the world. If Nyiragongo erupts, there's no way to outrun the lava. At over 60 miles an hour, it can flow faster over the ground than any other lava. Next morning, and the lake is calmer. Dario watches another scientist approach the lava lake to collect a sample. The special suit he wears will deflect some of the incredible heat at the lake's edge. But nothing can protect him if he comes into direct contact with the lava itself. Lava begins to bubble over the crater wall.
It is dangerous in my opinion. It is a little crazy. I mean, I won't do that. It's very, very close. Just on the rim. It's crazy. Oh my God. Come back. It's too long. Come back.
In Dario's eyes, this scientist is taking a big risk.
C'est pas la peine de rester là pour si longtemps. Ça fait déjà 5 minutes. C'est très dangereux.
The lake is becoming more active. The lava surges over the edge. The scientist retreats. As the lava flow ebbs, he collects a sample from the foot of the crater, where the lava has cooled and solidified into rock. Samples are sent to the University of Rochester in New York State for analysis. Geochemist Tom Dara will analyze the sample.
produced by both pressure and by furnace. So.
Gases and minerals are trapped inside. The sample is crushed. Then heated. That will allow the gases to escape from the rock so they can be analysed. The results are ready. Tom can now identify where the lava comes from.
The gases that we analyze, that trapped in the lavas collected from Mount Nyiragongo, tell us that this volcano is sourced from a very deep location within the Earth. The source has to be somewhere well below the Earth's crust.
Some scientists believe the chemical composition suggests that it comes from the very bottom of the mantle, 1,800 miles below. We can see what is happening on the virtual Earth. An enormous upwelling of intense heat, a mantle plume, is rising from the interior of the planet under this part of the Rift Valley. In the future, it could cause more volcanoes and earthquakes. The familiar landscape of the Rift Valley could change forever. New mountains could rise and new valleys form. Africa could be transformed. There is another way of getting a sample from the mantle. Far less dangerous. The High Street. Diamonds. Cut and polished like this, they look beautiful. Formed under extreme heat and pressure, they're brought to the surface by volcanic eruptions. Magma surges upwards, carrying the diamonds. Many get stuck along the way. A few make it close to the surface. Even fewer will make it into our hands. As we can see on the virtual Earth, these events are rare, and diamonds are only found in a handful of places around the world. Diamonds and volcanoes are not the only thing we get from the mantle. In some places around the world, the heat within the Earth can be put to work for us. This is Iceland. The heat transferred from the mantle provides an almost limitless source of energy. The crust in Iceland is thin. In some places, only 6 miles thick. As water seeps down into the crust, it heats up and quickly turns to steam. Power stations capture the steam and use it to generate electricity. Iceland is cold, just a few miles from the Arctic Circle. Yet this power makes some surprising things possible. All year-round swimming. Icelanders heat this small bay with thermal energy. The seawater beyond is a freezing 4 degrees below. But within the bay, swimmers can relax in a comfortable 29 degrees Celsius. Almost all the country runs on geothermal power. In Iceland's capital city, Reykjavik, almost every home is heated using this geothermal power. In winter, they use it to heat the streets and pavements to keep them ice-free. An almost limitless free source of energy. The virtual Earth can reveal more secrets of the Earth machine. The machinery of the Earth is driven by heat from the Earth's interior. This comes from far beneath the surface of the planet, beneath the crust, the part we live on, rely on, beneath the mantle, the source of volcanoes. Nearly 2,000 miles down lies the planet's generator, a planet within a planet. A vast sphere made of molten metal. This is the outer core. It's hot, very hot. Between 3,000 and 6,000 degrees Celsius. This ball of molten metal does something special. It generates a magnetic field. This is no ordinary magnetic field. This one extends tens of thousands of miles into space. The only way to convey the true scale of this field is to shrink the virtual Earth in the hangar. The Earth's magnetic field is normally invisible to us, but there is a way to see it in action. These are the Northern Lights. Over the snow and ice of the Arctic Circle, a magical procession of lights dance across the night sky. This is the Earth's magnetic field made visible. It is vital for the survival of life on Earth. And this is how the magnetic shield works. The Sun is continually throwing out billions of atomic particles. They arrive above our atmosphere and are deflected away by the magnetic field. The Northern Lights are how we see some of those particles from the Sun interact with the field and our atmosphere. This incredible space shield is generated nearly 2,000 miles beneath the surface by the outer core. The field protects life on Earth. The magnetism of the Earth gives us north and south, east and west on our compasses. There are other, more surprising benefits. The North Atlantic Ocean. Thousands of miles of cold, deep, storm-tossed seas. One little marine creature will swim tens of thousands of miles through this massive expanse of water in its lifetime. Yet at all times, it will know its exact location and can navigate its way from here on the shores of North Carolina all the way across the ocean and back. The question for scientist Ken Lohman is, how do they do it? These young loggerhead turtles live at the University of North Carolina. Ken Lohman has devised an experiment to see just how turtles use the Earth's magnetic field. But to do so, this young turtle needs to dress up.
These are the little bathing suits that we've produced for the turtles. They're cloth harnesses that encircle the carapace, or the shell, but they don't prevent the turtle from moving its flippers in its normal way.
These harnesses are linked to this water tank. Ken uses an electric current to create a magnetic field around the turtle's tank. With the field turned on, the turtle instinctively knows which way to go.
If we were to reverse the magnetic field that the coil is producing, the turtle in all likelihood would turn around and swim in the opposite direction.
And as soon as Ken changes the magnetic field, the turtle changes direction. So the turtles really are sensitive to the magnetic field. It's down to a mineral called magnetite.
Magnetite is a magnetic mineral. It's actually the same mineral that compass needles are made of. And it appears likely that the turtles use magnetite crystals in their heads to perceive the magnetic field.
Ken found that the turtles could do far more.
They can use the field not only as a source of directional information, but also as a way of figuring out where they are within the ocean. So in effect, they have a global positioning system that is based on the Earth's magnetic field.
Anywhere within the enormity of the world's oceans, this tiny turtle knows exactly where it is. And that's how this turtle is able to swim out into the Atlantic and then, years later, find her way back to this exact beach. It's all down to the magnetic field generated by the outer core deep within the planet. The Earth machine is in constant motion, creating effects on the Earth's surface and beyond. The source of its power lies beneath the crust, through the mantle and below the outer core. We are now more than 3,000 miles into the Earth. This is the final destination, the center of the Earth. It is called the inner core. It too is made of metal, but this is now solid, crushed by pressures around 4 million times greater than on the surface of the planet. It's super hot, a staggering 6,000 degrees Celsius, the same temperature as the surface of the sun. And it is this heat that is the key to how the Earth machine works. All the volcanoes, the earthquakes, the never-ending movement of the land, it's all powered by this huge fiery ball of solid metal spinning over 3,000 miles below. The inner core is the engine of the whole planet. And it works like this. Heat rises upwards from the inner core in vast plumes. When they reach the Earth's crust, they fan out. This pushes the Earth's tectonic plates across the face of the planet. Then these plumes of heat cool and fall back to start the cycle all over again. Many scientists believe this cycle will continue until all the continents are forced together into one huge landmass. In 250 million years, there will be no more America, Russia, or China, but one giant supercontinent. Unimaginable change, and all powered by that giant ball of metal over 3,000 miles beneath our feet.